give or complex valued function, complex valued function w is equal to f of z is defined and differentiable, is defined and differentiable at each point, uh, each point in a domain. What do we mean by domain? Domain is the set from which your function w is equal to f of z takes the value. Okay, so if f of z is defined from disk, then that disk is called the domain of the function f of z. Then it is called is called analytic. There are two to three different names. Analytic, or the function can also be termed as regular or holomorphic. All three names represent that the function w is equal to f of z is differentiable at each point in the domain. Yesterday we stopped with an example, and I would like to recall the example. So example f of z is equal to mod of z square. What we saw at the end was this function is differentiable only at 0 comma 0, otherwise not differentiable. So by this information and the above definition, what the above definition says, it must be defined as well as differentiable at each point in the domain. Okay, so on the complex plane, I'm defining this function. Here is the point 0 comma 0. Only at this point it is differentiable, whereas any neighborhood if you take, it is not differentiable. So this turns out to be not analytic. Okay. Whereas we also saw another example, f of z is equal to z cube. Second, f of z is equal to z cube. For this, we saw that yes, it is differentiable at z is equal to I. So if you take any neighborhood of I, in that way you will see that z cube. Even if you take any neighborhood of I, in that case, your function will be defined and differentiable. So I can say that is analytic at z equal to I. Okay. So this is the meaning of analytic function. By analytic function, I mean that it has to be defined and differentiable, but not at that point, at each point in the domain. Okay. So as we are looking at 0, 0, so if you take any small circle around 0, 0, in that circle at every point it has to be differentiable. There must be at least one circle around this I in which your function becomes differentiable at each point. Then I will say that the function is analytic. So checking out the derivative for every function every time using limit, this is quite a difficult task, and uh, is not actually a convenient way of doing it. So what is done is there is this theorem which talks about the analyticity of a function just using two conditions. And the theorem is, I will write down the theorem. The necessary and sufficient condition, the, the necessary and sufficient condition for a for continuous complex valued function w is equal to f of z, and we have seen yesterday that every f of z can be written as u of x comma y plus I times b of x comma y. To be analytic, to be analytic, to be analytic in a region R, in a region R, R, ux, uy, bx, by are continuous. What do I mean by ux, uy, vx, vy? So u is the derivative of u. What is u? The real part of your answer. Derivative of this real part with respect to x, derivative of real part with respect to y. Derivative of imaginary part with respect to x, imaginary part with respect to y. So these are continuous, and with that ux is equal to vy and uy is equal to minus vx at each point in the region R. Okay. So this condition 2, this condition ux is equal to vy and uy is equal to minus vx. So condition 2 is called CR equation. The full form is Cauchy-Riemann equation. In bracket CR equation. So a function to be analytic, it must satisfy the CR equation. What are the CR equation? Ux equal to Vy and Uy is equal to minus of Vx. So if this condition is satisfied in a given region, then what we say is that the function is analytic in that region. And what about the derivative? When f of z is analytic, so we'll down a note. If f of z is analytic, f of z is analytic, its derivative is given by its derivative is given by one of the following one of the following expression. f dash of z is equal to ux plus I times vx. F dash of z is equal to vy plus I times vx. Or f dash of z is equal to ux minus I dy. F dash of z is equal to vy minus I v uy. Yes, can anyone tell me, are they different, all four of them? Do they look different? So by CR equations, if you use ux equal to vy, so in the first term, in the second one, vy is given. So all four expressions are not different, but those are all are one and the same. You are just using the CR equation and writing different expression. Fine, we'll go for the example. Show that the following functions are analytic. First one, e to the power z. So first of all, in order to check the analyticity, what we do is we check the CR equations. If the CR equations are satisfied in a given domain or around in all of the complex plane, then I will say that the functions are analytic. So what are the CR equations? I will write it down here in the bracket on rectangle. Ux equal to Vy, Uy is equal to minus of Vx. This condition needs to be satisfied, and for that I will need u and v. So let's separate u and v. E to the power x plus iy. Separate this, e to the power x, e to the power iy. Again, iy can be written as cos y plus I e raised to x sin y. So from this expression, u is equal to e to the power x cos y, and v is equal to e to the power x sin y. What is ux? Ux is when I take the derivative with respect to x, this you must have seen in your bridge course. I'm taking the derivative of u with respect to x. So this will become constant. Cos y is constant. Derivative of e raised to x is e raised to x. Ux. What is vx? Derivative of v with respect to x. Sin y becomes constant. E raised to x का derivative e raised to x sin. What is u with respect to y? Now when I take the derivative with respect to y, x will become constant. So minus e raised to x sin y. What is Vy? Derivative of v with respect to y. e raised to x cos y. Now you can verify that ux is equal to e raised to x cos y, which is equal to v with respect to y. First CR equation is satisfied. What is uy? Uy is equal to minus of e raised to x sin y. But what is e raised to x sin y? It is minus of v x. So both the conditions are satisfied. CR equation satisfied. Okay, let's go to the next example. F of z is equal to z cube. Okay, so since I want to check it, what I will do is x plus iy raised to 3. Make the cube of this x cube plus 3 times square yy plus 3x iy square plus iy cube. X cube plus I in bracket 3x square y. I square is minus 1, so this will become minus 3x y square. I cube is minus I y cube. So the real part is x cube minus 3x y square plus I into 3x square y minus y cube. So u is equal to x cube minus 3xy square. V is equal to 3x square y minus y cube. And so ux, this will be 3x square minus 3y square. U with respect to y is minus 6xy. 3x is 6xy and vy is equal to 3x square minus 3y square. So from this we can see that ux equal to vy. So observe ux equal to vy and uy is equal to minus of vx. CR equation satisfied. And this is not just satisfied at a particular point. CR equation are satisfied for any value of xy. So CR equation are satisfied in complete plane, and so f of z is equal to z cube is analytic. Fine. So next example, and this is a very important example as it characterizes the necessary and sufficient conditions, will help you understand what we mean by one-way statement. And the question is, show that f of z is equal to under root mod of xy is not analytic at origin. At origin, although CR equation satisfied, although CR equation satisfied at origin. So what is happening here? CR equations are satisfied, but still the function is not analytic. And what is the reason here? So the reason is, I will go by, I mean, recall the statement of that analyticity. It said that all the four uh, partial derivatives are continuous and their equations are satisfied at every point in the neighborhood of the point. Okay, so you take a point at origin, say for example in this, so at 0 0, CR equation must be satisfied, but it also has to be satisfied in the neighborhood of 0 comma 0. So if CR equations are not satisfied in the neighborhood, then we cannot declare that CR equation, I mean, the function is going to be analytic. What is the actual meaning of analytic? Analyticity is the derivative must exist and it must be completely defined. So in this example, what we need to show? We need to show that yes, CR equations are satisfied at the origin, but the function is not analytic, which means that it is not differentiable at the point 0 comma 0. So let's go ahead with this. So what is f of z? F of z is equal to under root mod of xy. Look at this. This is just the real part. Okay, there is no imaginary part to this. So u is equal to under root mod of xy and v is equal to 0. So how do we define the partial derivative of u with respect to x? Since there is mod, I should go by limit x tends to 0. Derivative is with respect to x, x tends to 0. U of x comma 0 minus u of 0 comma 0 upon x. So if you put y equal to 0, what do you get? 0 minus 0 upon 0. This is actually, I shouldn't write this. This is a wrong way of interpreting this or saying like this. X is tending to 0, the denominator is not exactly 0. So what we will do here is I'll write it down as directly as answer 0. Then uy, partial derivative of u with respect to y is limit x tends to 0, sorry, y tends to 0, u of y comma 0, 0 comma y minus u of 0 comma 0 upon y. Again, the answer turns out to be 0. So Vx will be 0 as V itself is 0, derivative of V with respect to x is 0. V with respect to y is 0. So what do we observe? Ux is equal to Vy. Both of them are 0, this term and this term. Even Uy is equal to minus of Vx, as both of these terms are 0. So CR equation satisfied at 0, 0. From this CR equation satisfied at 0, 0. But now we will show that it is not differentiable. How do we show that? We'll use our basic definition. What is our basic definition? F dash of 0 is equal to limit z tends to 0 f of z minus f of 0 upon z minus 0. This is equal to limit z tends to 0 under root of mod of xy. What is f of 0? It is 0 upon z, which is nothing but x plus I. So we have come again to the concept of the path. So you have a x and y axis, the real axis, imaginary axis. This is z equal to 0. So I can reach this point 0 from uh, any of the paths, and out of this I will consider the straight line. The equation of the straight line passing through origin is y equal to mx. So I will consider if I am reaching the origin along the path y is equal to mx. So let z tends to 0 along the path y equal to mx. Okay. So when we put this, so as z tends to 0, x has to go to 0. So limit of this will turn out to be x tends to 0. In the numerator, y has to be equal to mx. So that will become m into x square under root mod of m into x square upon y is equal to mx. So x will come outside 1 plus I m. Again, I can take x square out of the mod since x square is of course positive, and that the root will get cancelled out with this. And so finally what do we get here is this is equal to the root of m upon 1 plus I m. So what does this mean? This means that the limit depends on the slope of the line. So if I change the slope of this line m, the limit will change. But what we know from our previous studies is limit is unique. So it must have a unique value which should not depend on the slope of the line. And that's why f dash of 0 does not exist. Function is not differentiable and hence it is not analytic. F dash of 0 does not exist. So the function is not analytic. Any problem here? You can ask or I'll go ahead. Fine. No problem at all. Then I'll go ahead. Determine the constant A, B, C, D. If if f of z is equal to x square plus 2axy plus by square plus I in bracket x square plus 2dxy plus y square is analytic. So if the function is analytic, it must satisfy the CR equation. So I will write down u. U is nothing but x square plus 2axy plus by. Just v. V is nothing but x square plus 2dxy plus y square. So ux is equal to 2x plus 2ay. What is uy? Uy is 2ax plus 2by. What is vx? What the heck? Oh, this is cx square. I'm so sorry. So vx is 2cx plus 2dy. Vy is equal to 2dx plus 2y. So we have ux equal to vy. This is true if the function is analytic, and uy has to be equal to minus of vx. So I will compare the terms. Is ux 2x plus 2ay has to be equal to 2dx plus 2y. So 2 will get cancelled out. So dx minus x plus y minus ay equal to 0. And uy is equal to minus vx. So what do we get? 2ax plus 2by is equal to minus of 2cx minus 2dy. Again 2 gets cancelled out. So ax minus cx, a plus c times x, then d plus d times y equal to 0. So from this, you can solve the two equations, and I think there must be infinitely many solutions to this. Out of that infinitely many, you can put a equal to 1, will get minus 1 equal to minus 1 and equal to. Okay. So this type of MCQs can be asked in your online exam. I'll give you some of the homework for which you can verify whether the functions are analytic or not. So determine whether this is homework. Determine whether the given functions are analytic. First one, cos of z. Second, 1 upon z. Third one, z square minus z bar. Fourth one, e to the power x in bracket cos y minus I sin y. And fifth one, x square minus y square plus 2i xy. You can check the analyticity for the four functions. Now I will talk about the analyticity in the polar coordinates. So I told you that every complex number can be represented in three ways. The first one is x plus iy. The same complex number can be written as r in bracket cos theta plus I sin theta. This is called the polar form. And the third one is r e to the power I theta, Euler form. Okay. So this too generally deals with r and theta. This r and theta, every complex number denoted by r comma theta. This is called the polar form. So any equation or the function, complex function, can also be given in the polar form. Say for an example, f of z is equal to r plus I times theta. This is a function of a complex number whose value is again a complex number. This is complex valued function. And I want to check this function is what you say analytic or not. How do we do that? That can be done using the CR equations in polar form. So CR equations in Cartesian form is ux equal to vy, uy is equal to minus of vx, and CR equations in the polar form are given. So I will write it down here. CR equations in polar form. U r equal to 1 upon r v theta, and the second one vr is equal to minus 1 upon r u theta. Okay. So in the polar form, what we will do is we will find u in terms of r and theta. I will find out v in terms of r and theta, and I will similarly check the CR equations whether those are satisfied or not. So quickly one example, find P if f of z is equal to r square cos theta, cos 2 theta actually, plus I r square sine of p theta is analytic. What do you observe, or what we observe? we observe that u and v are given in terms of r and theta, which means that we are working in polar coordinate system. So if we are in polar coordinate system, CR equations to be used should be polar. So u is r square cos of 2 theta, v is equal to r square sine of p theta. What is u with respect to r? Is 2r cos of 2 theta. U with respect to theta is minus 2r square sine of 2 theta. V with respect to r is 2r sine of p theta. V with respect to theta is p r square sine of p theta. Now use the given equation in which you will get the value of p. We need the value of p, remember that. So VR and u theta. So ur is equal to 1 upon r v theta. ur is equal to 1 upon r v theta by CR equation. So I will put the values in this. What is ur? ur is 2r cos of 2 theta, which is equal to 1 upon r p r square sine of p. So 2r square will get cancelled out. Oh, sorry, 2 will remain as it is. This r square and r square will get cancelled out. Cos of 2 theta is equal to p sine of p. Okay. ur is equal to 1 upon r v theta. Oh, sorry, I've written this wrong. V with respect to theta has to be p r square cos of 2 theta. This has to be cos. But, how can we compare? This will be cos. So this two can only be equal if p is equal to. So like CR equations in Cartesian form, we also have the CR equations in polar form. Fine. So in the next lecture, what we'll see is we'll study the harmonic functions. What do we mean by harmonic functions and how to deal with harmonic functions. Please put your name and roll number in the chat box. If you have any difficulties, you can ask, or else